Good afternoon. Today I will talk about a measurement of the strength of the spin-orbit interaction in iron cobalt boron nanomagnet and how this strength depends on electrical current and more specifically on the current-induced spin accumulation. My name is Vadim Zayats. I'm from IST Tsukuba, Japan. This work was done in collaboration with Kyiv University, Ukraine. Before I will show you how to measure the strength of spin-orbit interaction, I would like to mention some important facts about spin-orbit interaction. The first fact is that the spin-orbit interaction is a relativistic effect. It means that spin-orbit interactions describe the fact that an electron, which moves in an electrical field, also experiences a magnetic field. It is due to the relativistic nature of electromagnetic field. The second fact is that spin-orbit interaction is fully characterized by the relativistic magnetic field, which is called magnetic field of spin-orbit interaction. It's absolutely real magnetic field and is undistinguished from magnetic field of any other source. I should note that quantum field of electron experience a similar relativistic effect, which is described by Dirac equations. This relativistic effect also contributes to spin-orbit interaction, but this contribution has the same symmetry and therefore can be included into magnetic field of spin-orbit interaction. The third fact is that in general spin-orbit interaction is a small effect because of its relativistic nature and can be substantial only in proximity of atomic nucleus. There are two reasons for that. As you can see, magnetic field of spin-orbit interaction is proportional to electron speed and electrical field. Therefore, the first reason is that the electron field is very large in proximity of atomic nucleus because of very small size of the nucleus. The second reason is that the speed of the orbital movement is really fast. From this famous relation, the electron movement speed in the first orbital of hydrogen atom equals to fine structure constant. As you can see, the electron moving speed along the orbital is already close to the light speed, which is good for a relativistic effect. Fourth fact is that spin-orbit interaction requires an external breaking of the time-inverse symmetry. Spin-orbit interaction cannot break time-inverse symmetry by itself alone. It makes the magnetic field of spin-orbit interaction to be proportional to external magnetic field. Next, I will explain how we measure the strength of spin-orbit interaction. The measurement is direct and relatively simple. In equilibrium, the magnetization is held along the magnetic z-axis by internal magnetic field, which is sum of demagnetization spin-orbit and magnetization magnetic fields. We have applied an external magnetic field perpendicular to the z-axis. It tilts the magnetization. External field, which is required to turn the magnetization fully in plane, is called anisotropy field. The larger the internal magnetic field is, the larger the field is required to turn out the magnetization, and therefore the larger the anisotropy field is. Additionally, we have applied an external magnetic field along the z-axis. This external magnetic field makes it even harder to turn out the magnetization, and therefore makes the anisotropy field larger. Also, external magnetic field makes magnetic field of spin-orbit interaction larger because spin-orbit interaction is proportional to total external magnetic field. As a result, the measured anisotropy field is linearly proportional to external magnetic field Z, as described by this formula. By fitting external data to this equation, coefficient of spin-orbit interaction is evaluated. This equation is obtained from minimizing the total magnetic energy. The step-by-step detailed mathematics how to obtain it can be found in this PDF file or in my website. We use a Hall setup to measure magnetization angle in iron cobalt boron nanomagnet. Equilibrium magnetization of all studied nanomagnets was perpendicular to plane. Nanomagnets of different thickness, composition, and size are measured. Smallest size was 50 by 50 nanometers. Largest size was 3 micrometer per 3 micrometer. All details of the measurement are explained in this YouTube video. This graph shows a measurement of anisotropy field versus external magnetic field. As we expected, anisotropy field linearly increases under external magnetic field. If we expand the lines to zero anisotropy field, we obtain the value of internal magnetic field, the magnetic field which holds the magnetization along its z-axis in absence of external magnetic field. Back to measurement of strength of spin-orbit interaction. As you can see from this formula, a plot of difference between anisotropy field and external magnetic field is more informative. This graph shows this difference for single-layer and multi-layer nanomagnet. As you can see, in both cases dependence is linear, with some oscillation on top of it. The slope of graph gives the value of coefficient of spin-orbit interaction. It is small and negative for single-layer nanomagnet, and large and positive for multi-layer nanomagnet. It is a systematic dependency. This graph shows a measured coefficient of spin-orbit interaction versus anisotropy field. Each dot corresponds to a measurement of one individual nanomagnet. The dots of the same color and shape correspond to nanomagnets fabricated on the same wafer. The stars are used for multi-layer nanomagnets. As you can see, coefficient of spin-orbit interaction is always large for multi-layer nanomagnet. In contrast, coefficient of spin-orbit interaction is small, often negative but sometimes positive for single-layer nanomagnet. So our first finding is that spin-orbit interaction is stronger in multi-layer structure. It means the contribution of bulk of iron-boron nanomagnet to spin-orbit interaction is negative and small, and interface contribution is positive and large. The bulk contribution dominates in single-layer nanomagnet. The interface contribution dominates in multi-layer nanomagnet. The second finding is the strength of spin-orbit interaction substantially depends on the roughness and sharpness of interface. This is the same graph, but only multi-layer iron-boron tungsten nanomagnets are shown. As you can see, the strength of spin-orbit interaction steadily increases when the number of iron-boron layers increases, till the number of layers exceeds 6. For larger number of layers, coefficient of spin-orbit interactions drops. For our sputtering machine, the surface roughness of each consequent grown layer becomes worse. As a result, after the number of layers exceeds some critical number, the interface contribution to coefficient of spin-orbit interaction becomes smaller. The bulk contribution dominates, and in total, coefficient of spin-orbit interaction reduces. This slide explains the reason why coefficient of spin-orbit interaction can be either negative or positive. In vacuum, the spin always aligns exactly along the external magnetic field. In nanomagnet, the external field also creates spin-orbital magnetic field. When this spin-orbital field is directed along the external field, the coefficient of spin-orbit interaction is positive. When the spin-orbit field is directed opposite to external field, the coefficient of spin-orbit interaction is negative. Next, I will talk about oscillations which exist on the top of these linear dependencies. Our third finding is that the oscillation is a feature of interface. It is because the amplitude of oscillation is smaller for thicker nanomagnet when the bulk contribution is larger. The oscillation amplitude is larger for thinner nanomagnet or multi-layer nanomagnet when the interface contribution is larger and dominates. It can be more clearly seen from this graph, which plots measured dependence of oscillation amplitude on coefficient of spin-orbit interaction. The linear dependence is clear, implying that both strength of spin-orbit interaction and oscillation amplitude increase simultaneously when there are more interfaces in nanomagnet and the interface quality is better. This graph shows a measured anisotropy field versus external magnetic field at different current density. Both the anisotropy field and strength of spin-orbit interaction are substantially modulated by current. There is a difference between lines even in absence of external magnetic field. Coefficient of spin-orbit interaction proportional to the slope of these lines. The slope of lines depends on the current. As you can see, the gap between lines decreases for single-layer nanomagnet and increases for a multi-layer nanomagnet. This graph shows measured anisotropy field versus current density in absence of external magnetic field. In case of single-layer nanomagnet with weak spin orbit, the current-induced change of anisotropy field is small, of only 0.2 kGauss, but it's linearly proportional to current. In contrast, in case of multi-layer nanomagnet with large spin orbit, the current-induced change is substantially larger, of about 1 kGauss, but is proportional to square of current. I would like to remind you that effective paramagnetic mechanism or magnetization reversal can occur only in the case of linear current dependency of anisotropy field, and therefore can be used only in this case. I just explained only a few of many interesting measured properties of spin-orbit interaction in iron-cobalt-boron nanomagnet. You can find more details about this measurement in this set of videos. Additionally, there is an explanation why the officially accepted interpretation of second harmonic measurement is incorrect and how to remove several systematic errors of this measurement. There is an explanation why the recent introduction of the field-like torque is incorrect and unjustified, and why the introduction of field-like torque violates several conservation laws of physics. We sincerely recommend using this measurement method of spin-orbit interaction in your lab. The measurement and measurement setup are relatively simple. Whether you are making a memory device or sensor, a measurement of spin-orbit interaction will allow you to optimize the device design and fabrication technology.